In this section, now that we've already talked about the definition of determinants and calculated a few examples by hand, I want to present to you a useful lemma, and it consists of 4 parts. And this lemma is basically going to give us some easier ways to compute determinants in certain situations. So I also, once I present the lemma to you, I also want to, 1, talk about why it's true, and then 2, show you how this lemma can be useful. So let's go through it. So part 1 says that if A has a row of zeros, then its determinant must be 0. Part 2 says that if A has 2 identical rows, then its determinant has to be 0 as well. So 1 and 2 are giving you 2 easy checks to say that the determinant is 0. If you find a row of zeros or 2 identical rows, then that's an easy check to tell you that the determinant is 0. Part 3 says that a matrix is nonsingular if and only if its determinant is nonzero. So nonsingular if and only if nonzero determinant. And this is something we were hinting at before when we were talking about motivation of determinants. We wanted the determinant to tell us whether or not a matrix is invertible. And so this is really confirming that our definition is a good one and doing what we wanted it to in the first place. And part 4, the last part, says that if A is in echelon form, then the determinant is the product of its diagonal entries. So this is also really, really useful, especially in computations. It basically is telling you that you don't have to row reduce it all the way to the identity matrix to figure out the determinant. You can just row reduce it to a echelon form matrix, and then look at the product of the diagonal entries in that echelon form matrix to help figure out what your determinant for your original matrix is. And this is especially useful because it is true, it is a fact that there are row operations taking A into an echelon form matrix, where specifically those row operations, we can choose to avoid multiplying rows by nonzero scalars. So that tells us that the only things that we really have to do are check how many times we swapped rows in those row operations to get to the echelon form matrix to figure out what the sign of the determinant is equal to. And I'll talk more about this later at the end in a specific example, but just have it in your mind that this is a really, really useful tool, especially for computers. This is actually how computers compute determinants a lot of times. It's very computationally efficient. Okay, so let's talk about why this lemma is true. So I still have some leftover scratch work from my last take, which did not go so well. But anyway, let's talk about the proof of the first one. So A has a row of zeros, and we want to show that the determinant is equal to 0. So let's say that row I is that row of zeros. Okay, so by our definition for determinant, I am allowed to do any number of row operations, including the row operation where I multiply a row by a non-zero scalar, such as 2. And in this case, I'm multiplying my row of zeros by 2. What does that do? Well, it doesn't do anything because 0 times 2 is equal to 0 still. So if I do this row reduction, I get back to the same matrix A. This row operation does not change my matrix. So then by the definition of determinants, the determinant of the new matrix that I get, which is just A itself, is equal to 2 times the determinant of the previous matrix that I had, which is also A. So the determinant of A is equal to 2 times the determinant of A. And so, of course, you could just subtract the determinant of A on both sides and get that the determinant of A is equal to 0. And that gives us what we want. Great. So now let's talk about part 2. If A has 2 identical rows, then the determinant has to be 0. Why would that be true? So let me zoom in a little here. So let's say that row I and row j are identical. Then let's row reduce A by adding negative row I to row j and replacing. What'll that end up doing? Well, if I add negative row I to row j, since these two rows are equal, then my new row j will have a row of zeros. So this row reduction results in a matrix B with B's row j, just a row of zeros. So the determinant of B is equal to 0. And because the row operation that I did here was I added a scalar multiple of one row to a different row, then I did not change the determinant at all. And therefore, the determinant of A is equal to the determinant of B, which is 0. And therefore, the determinant of A is 0. So that concludes that part of the proof. We have two equal rows, and then, excuse me, this is not scrolling for some reason. There we go. Right, so we have parts 1 and 2 out of the way. And now part 3 says that if A is non-singular, then the determinant is non-zero, and conversely, if the determinant is non-zero, then if the determinant is non-zero, then the matrix must have been non-singular to start with. So, how do I show that? Well, there's 2 parts to show there. So, first off, let's say that if A is non-singular, then A row reduces to the identity matrix. And the only row operations that you can do there are adding k times row I to row j and replacing. You can multiply some row by a scalar not equal to 0, and you can swap rows. And what effect do these have on the determinant? Well, this one has no effect. If I add rows to other rows, that does not change the determinant at all. So that one's fine. If I do this one, if I multiply a row by a non-zero scalar, then that multiplies the determinant by that same non-zero scalar k. In particular, if the determinant of A is not equal to 0, then the determinant of the next matrix should also not be equal to 0. And vice versa, if the determinant of the matrix that you row reduce to is not equal to 0, then the determinant of the previous matrix is also not equal to 0. Maybe if you're not completely convinced of that, the reason would be, well, you can just row reduce backwards, so you can row reduce from the identity matrix back up to A, or whatever. If A row reduces to B via this row operation, then B row reduces to A by dividing row I by k, which you can do because it's not 0. And the last thing that we can do is we can swap rows, and that just multiplies the determinant by -1. So anyway, since a row reduces to the identity matrix and the identity matrix has determinant not equal to 0, then A had to also have determinant not equal to 0. Great. For the other direction, I could assume that the determinant is non-zero and show that A is non-singular, or I could show the converse of that, which is what I'll do. I'll say that if A is singular, then I want to show that the determinant of A is equal to 0. So A is a square matrix. It is singular. That tells us that A is row equivalent to some matrix B in reduced echelon form, where B has a row of zeros. Then the determinant of B is equal to 0. So the determinant of A must also be equal to 0, just by the same arguments that we talked about up here. You could just reverse all the row operations to go from the determinant of B to the determinant of A, and none of these row operations would change whether or not the determinant is equal to 0. Okay, so that's it for part 3. How much space do I got? Good amount of space. Great. Part 4 is if A is an echelon form matrix, then its determinant is the product of the diagonal entries. So let's assume A is in echelon form, and I want to show that its determinant is the product of the diagonal entries. That does not mean that it's the product of the pivots, but those end up being true if the pivots are all, if A is an invertible matrix, then the pivots will all be non-zero. So I can split this into two cases where all the pivots are not equal to 0, or the case where at least one of them is 0. Those cases are essentially, or effectively, those cases are exactly the cases where A is either singular or non-singular. So for case 1, let's suppose A is a singular matrix. Then A has a row of zeros. Hence, one of its diagonal entries is 0. So the product of its diagonal entries is also 0. So the determinant of A is equal to 0 because it's a singular matrix, which is equal to the product of its diagonal entries. Okay. So let's do it for non-singular matrices next. So suppose A is non-singular. So we're already assuming that it's in reduced echelon, that it's in, not reduced echelon form, that it's in echelon form. So it looks something like this. So I'll do A1, A2. up through an for my diagonal entries. Everything below the diagonal is going to be 0, and everything above the diagonal will be something, some random number. These, I'm just going to put stars for this. The stars could be 0, they could be non-zero, they could all be different, they could all be the same. The star just means that it doesn't matter what number is up there. The argument that follows is going to be the same. What you can do is you can do row operations to take this matrix to the diagonal matrix with the same diagonals, and 0 is all below and 0 is all above. And the only row operations that you have to do that are just adding k times row I to the row to rows that are above row I. So basically what I'm saying is that I can add I can add a scalar multiple of this row, add that to row 1 to make the entries above it all equal to 0, and you could do the same for row 3, row 4, all the way up through row n to make all of the entries above it equal to 0. And the only row operations that you're doing to do that don't change the determinant at all, which is key. So the determinant of A is equal to the determinant of this diagonal matrix. I haven't changed the determinant at all here. Okay, so now let's maybe copy and paste this over here. Okay, now what can I do? Well, I can multiply each row by 1 over AI, and since A is non-singular, then each AI is not equal to 0. That was actually necessary for the previous step as well, for each AI to not be equal to 0, but that is true because it's non-singular. So I can do this, and when I do that, what I end up with is the identity matrix. So the determinant of A is equal to 1 over A1 times 1 over A2 times 1 over AN times the determinant of the identity matrix, which of course is equal to 1. Oh, I messed up, I think. Wait, yeah. So the determinant of A is equal to no, okay. I reversed this. It should be the other way around. The determinant of the new thing is 1 over, there we go, this is right. So the determinant of the new thing that I get, which is the identity matrix for us, is equal to, I'm multiplying by all of these 1 over AIs times the determinant of my previous matrix. Since the determinant of the identity matrix is 1, then I can conclude by multiplying by A1 through AN on both sides that the determinant of A is just equal to A1 times AN, which is the product of its diagonal entries. And now we're good. Okay, cool. And now it's not scrolling. Let's back out again. All right, now it's scrolling again. Great. Sorry about the technical difficulties. All right, so now we're done with all that. Let's put a little box for finishing our proof here. So now I want to show you how I can use these things. So here are some things that I want to calculate the determinant of. This is an echelon form matrix. All of the diagonal entries are non-zero. So the determinant of this echelon form matrix must be equal to the product of its diagonal entries, which in this case is equal to 6. And so we don't even have to do any row reductions. We can just straight up say that the determinant of this guy is just 6. Okay, what about for this second guy here? I have 1, 2, 3, 2, 4, 9, 1, 2, 3. And so here we can recognize that the first and third rows are identical. And so we can apply, I believe that was part 2 of the lemma, to say that because there are 2 identical rows, then the determinant of this guy must be equal to 0. There is a more general fact here too. So if you could, if you had a matrix where, let's do like 1, 2, 3, 1, 1, 1, and then the third row will be like the first row plus the second row, 2, 3, 4. So the determinant of this guy is equal to 0, and I can see that just because this row right here is a linear combination of the other rows, and that would, so there are a lot of ways that you could explain why this must be 0. So one thing that you could say is like, oh hey, the rank of this matrix has to be less than 3 because this row is a linear combination of the other rows in it. So this is the row space is has dimension less than 3. In this case, it would be 2. So it's a singular matrix, so it would have to have determinant 0. Or you could just, you could see that this is true by, you could subtract this row from that, and you can also subtract this row from row 3. And that would tell you that this is row equivalent to a matrix with a row of zeros. And in general, if you can row reduce to a matrix with a row of zeros, then that will be a singular matrix and it will have determinant equal to 0. By the way, some notation. So notation. Instead of writing determinant of matrix, we will sometimes just write vertical bars for the determinant. And in particular, instead of writing this, so I don't mean that you would write, let me copy and paste this so this goes a little faster. You would not write this matrix with vertical bars around it. That's not what I mean. You would just replace those brackets with the vertical bars. And so a lot of times people will say oh, calculate this thing with vertical bars on either side of the matrix instead of square brackets. And that means that they're asking you to compute a determinant. And so this is really just shorthand. This just kind of simplifies things sometimes. Okay. All right, here's another application. Does the linear system 15x plus 40y equals 0 and 3x plus 8y equals 0 have 0, 1, or infinitely many solutions? So right away we can rule out at least one of these answers. Which one? Think to yourself, which one should it be and why? Well, it would be 0. It's impossible for there to be 0 solutions to this because this is a homogeneous system. So this is a homogeneous system which always has the 0 solution. Which means that if x and y are both equal to 0, then this system is completely satisfied. Therefore, it has to have at least one solution. So the question then becomes, does this homogeneous system have either one or infinitely many solutions? And the way that you could check this is by using determinants. And so the determinant of the matrix of coefficients for this, so the matrix of coefficients for this linear system is 15, 40, 3, 8. And the determinant of this guy is equal to 15 times 8 minus 3 times 40. That's our AD minus BC formula. 15 times 8 is equal to 3 times 5 times 8, which is 3 times 40. So I get 3 times 40 minus 3 times 40, which of course is equal to 0. So this determinant is equal to 0. So this is a singular matrix. Because it is singular, that tells us there are infinitely many solutions. All right, if you recall, the definition of a singular matrix is that the homogeneous system that it represents has infinitely many solutions. So that's our quick check to answer this question here. Okay. Last thing I want to do for this video is show you how to calculate this determinant right here more efficiently. So note that I'm using the vertical bar notation. So if I want to calculate this, I can just do row operations. So what I was saying before about being computationally efficient, I can always put something into echelon form by doing only row swaps and adding linear and adding, let me just write this down. Can get away with just doing row swaps. This should be a J, or K times row I plus row J. Adding scalar multiples of one row to other rows. We can get away with just doing these two matrices, and we don't have to multiply rows by non-zero scalars. So that is unnecessary. So let's do that. Okay, so this row right here, I'm going to use this to zero out the entries in the first column above it. So I'll do negative row 3, add it to row 1, and replace, and I'll do negative 2 row 3, add it to row 2, and replace. And this does not change the determinant at all, so this determinant is going to be equal to the determinant in the that I'm about to write. So this will be 0, 0, 2, 0, 4. Because this entry was a 0, then that's not going to change the entries above it, so that's nice. And okay, what are these two entries going to be? Well, I should have, so for row 1, I'm adding negative 4, adding that to 1, so that should be negative 3. And for row 2, I'm adding negative 2 times row 3 to row 2, so I'm adding negative 8 to 9, so I should end up with 1. Great, so this is the new matrix that I get. So this determinant is equal to that determinant. So these two things are in fact equal. And now I can do more row operations. I can use this one right here to zero out the entry above it. Let's do that. Let's do negative 3 times row 2, add it to row 1. And that won't change my determinant. And this should be a negative 6 because I'm adding negative 3 to that entry. Okay. And so this determinant is equal to that determinant is equal to that determinant, and this Next line, I'm going to swap rows 1 and 3. And when I do that, I'll get the negative of the determinant of this matrix. And this is an echelon form matrix, so its determinant is the product of its diagonal entries, which would be 2 times 1 times negative 6. And of course I'm taking the negative of that, therefore this determinant is equal to 12. So the determinant of the matrix that we started with, this guy right here, is in fact equal to 12. And I didn't have to multiply any rows by a non-zero scalar to get there. So that becomes really computationally efficient because the only things that we have to ever do are swap rows and keep track of how many times we swapped rows. And then all of these row operations don't change our determinant at all. So the process is row reduce to echelon form, take the product of the diagonals, and that's our determinant up to a possible change in sign if we swapped some rows. So we'll end it there. Thank you for listening.